Hi, this is the read aloud to Chapter 4, Lesson 2, Earthquakes and Seismic Waves. Witness to disaster on page 128. On May 12, 2008, a major earthquake struck China. American reporter Melissa Block was conducting a live radio interview in that country, and the moment of the earthquake struck. "What's going on?" Block asked. She remained on the air and continued. "The whole building is shaking. The whole building is shaking." Block watched as the ground moved like waves beneath her feet. The top of the church across the street started to fall down. For minutes, the ground continued to vibrate under Block's feet. The earthquake that day killed about 87,000 people. That is a very catastrophic number. What are seismic waves? Earth is never still. Every day worldwide, several thousand earthquakes are detected. An earthquake is a shaking and the trembling that results from movement of rock beneath Earth's surface. Most earthquakes are too small to notice, but a large earthquake can crack open the ground, shift mountains, and cause great damage. Cause of earthquakes: the force of plate movement causes earthquakes. Plates underneath the continents. Plate movements produce stress in Earth's crust, adding energy to rock and forming faults. We reviewed that last chapter. Stress increases along a fault until the rock slips or breaks, causing an earthquake. In seconds, the earthquake releases an enormous amount of stored energy. Some of the energy released during an earthquake travels in the form of seismic waves. Imagine yourself as a cartoon character and you have all of this stress and pressure and energy built up inside of you, and then you explode. Can you see the waves of energy coming out from your body? Seismic waves are vibrations that are similar to sound waves. They travel through Earth carrying energy released by an earthquake. The speed and the path of the waves is in part depend on the material through which the waves travel. Waves travel different through water as they do through land, as they do through air. So this, once again, are the layers of the earth: inner core, outer core, mantle, and then crust. Page 130, types of seismic waves. Like a pebble thrown into a pond, the seismic waves of an earthquake race out in every direction from the earthquake's force. The focus is the area beneath the Earth's surface where rock that was under stress begins to break or move. This action triggers the earthquake. The point on the surface directly above the focus is called the epicenter, so right in the middle. Most earthquakes start in the lithosphere within about 100 kilometers beneath Earth's surface. Seismic waves carry energy from the Earth's focus. This energy travels through Earth's interior and across Earth's surface. This happened in 2002 when a powerful earthquake erupted the Denali Fault in Alaska. That's shown in Figure 1. There are three main categories of seismic waves. They are P waves. P is for primary, which is first. S is secondary, S waves, and surface waves. And those are last. But an earthquake sends out only P and S waves from its focus. Surface waves can develop wherever P and S waves reach the surface. So they can be P and S waves underneath that we never feel. And then S waves are the only ones that you will feel on the surface. Page 131, these are examples. P waves are seismic waves that compress and expand the ground like an accordion. So they play an accordion, in and out, in and out, in and out. That would be primary. S waves are seismic waves that can vibrate from side to side. So they zigzag, in and out, up or down. The vibrations are at angles of 90 degrees when they travel. When S waves reach the surface, they shake structures violently, while P waves travel through both solids and liquids. S waves cannot move through liquids. So primary waves can move through solids and liquids. S waves, the secondary waves, cannot move through liquids. Surface waves, P and S waves reach the surface, and some of them become surface waves. They're more slowly than P and S waves, but they can produce severe ground movements. These are the wavy ones. They come up here and they shake and rattle the ground. That is the ones that cause the damage. They shake buildings from side to side and make them fall over. If you want to do this little chart on the side, they can vibrate the ground from side to side. Boom, boom, boom. They can make the ground roll like oceans, connected to whichever one you think is over here, and compress and expand the ground like an accordion. Or stretch it and expand it. You can fill those in. If you want to take some time, you can do 1A and 1B. Not requiring it. The movement of the magnitude scale, the moment magnitude scale, rates the total energy an earthquake releases. It's also called the Richter scale. Most earthquakes moment magnitude. To assign a magnitude to an earthquake, geologists use data from the seismographs and other sources. The data allows geologists to estimate how much energy the earthquake releases. Comparing magnitudes. An earthquake's moment magnitude tells geologists how much energy was released by an earthquake. Each 1 point increases in magnitude represents the release of roughly 32 times more energy. For example, a magnitude 6 earthquake releases 32 times as much energy as a magnitude 5. Information not significant to this chapter, but it does give you some numbers to say, wow, that's pretty strong. An earthquake's effect increase with magnitude. So the higher, anything below 5 is small damage. Anything above 6 can cause great damage. The most powerful earthquake with a magnitude of 8 or above are rare. In the 1900s, only 3 earthquakes had a magnitude of 9 or above. More recently, in 2004, Sumatra earthquake had a magnitude of 9.2. That was in the Indian Ocean. So you can look at these here. And page 134. What's the epicenter? How is the epicenter located? That is the middle point of the earthquake. When an earthquake occurs, geologists try to pinpoint the earthquake's epicenter. Why? Because they can locate and identify areas where earthquakes may occur in the future. Geologists use seismic waves to locate the epicenter. To do this, they use data from thousands of seismograph stations set up all over the world. However, you can use a simpler method by finding an earthquake's epicenter. Recall that the seismic waves travel at different speeds. P waves arise at a seismograph first, then S waves follow close behind. We're going to look at the graph, which we don't have to do. I just wanted to let you know that they find the epicenter by using the different speeds and rates of all of the readings from the seismographs. Suppose you know the distance of 3 seismograph stations. You can draw these 3 circles and they overlap. I'm pretty sure that's on our page 135. Yes. So the earthquake happened here. We took the reading from Chicago, from Houston, and from Savannah. And then they found where it actually happened right there in the middle. That's where the earthquake was. Determining an earthquake's epicenter. The map shows how to find the epicenter of an earthquake using data from 3 stations. And that's it for the chapter. I'm not going to get too in depth because it's self-explanatory. We're going to watch some videos on it on Friday. I appreciate you guys following along and learning. Feel free to answer these questions on your own if you would like. This is just the read aloud. Appreciate your time.